In this lecture, we will design a Chebyshev type of filter, and we will revisit Butterworth case, but this time we will try to take gain greater than 1. And for the Chebyshev, for the simplicity, we will try to make the gain is equal to 1. That means no DC gain here, and here DC gain will be there. So there are three things that we will study in this lecture. First is, as pointed out, we will design a Chebyshev active low pass filter, and we will keep the DC gain equal to 1. Then we will revisit Butterworth active low pass case, and this time we will make the DC gain greater than 1. So doing this, we'll introduce two more variables in the circuit, and there will be unfortunately only one equation, additional equation. And then finally we will see low pass filter circuit of second order, which is called multiple feedback topology. So up till now we have been using Salem key circuit to implement a second order low pass filter, but we'll see that this is additional circuit which can also be used for second order low pass filter. So first we will see the design steps that we will have to follow to complete the design of Chebyshev filter, and we will see that all the steps, they are going to be same as that of the Butterworth case. There will be only one additional step for the Chebyshev and one additional step for finite gain gain greater than 1 case. So of course the starting point will be given filter specification or template, and as was pointed out, we have to decide whether we want active or passive version. So we are going to take active version, and then we will have to see that for the given low pass filter specification, which type of transfer function we want to use, Butterworth or Chebyshev or elliptic one. So this will be decided again based on the ripple. If there is any ripple, then it's most likely going to be Chebyshev or maybe even elliptic also. In absence of ripple, it will be Butterworth. And as I pointed out, the first problem that we are going to consider is of Chebyshev type. So once it is decided that filter is going to be of Chebyshev type, the one of the parameters, additional parameters compared with Butterworth case that we will have to solve for is epsilon, which is the factor deciding the ripple. So we will have to first find out the ripple, and then we will have to find out the order of the filter. And for the Chebyshev case, now the calculation of order is going to be a little bit more complicated because the transfer function will contain now hyperbolic cosine functions. Then for higher order filters, of course, we will have to represent it as cascade of second and first order filters. So this we have already seen. And then we will have to pick up the various smaller transfer function from the table of the Chebyshev filter. But in this case, unlike Butterworth, where we had a single table for the Butterworth filter with, of course, various orders, this time there will be multiple table, and the table will be decided by ripple also. So based on the ripple, you will choose table, and then in that table you can pick the smaller h for the desired order of the filter. So first we will have to pick table based on ripple and then coefficient based on order. So here I have mentioned step 7, which we will not be taking for the Chebyshev case because gain is 1, but this will be required for Butterworth case where we are going to take gain is equal to 1. In fact, it will be required for Chebyshev also if you take gain greater than 1. So in this case, here we see that our overall filter is going to be cascade. And we have seen that the cascade will contain second order or first order filter. And each of these two filters, they can offer gain also. So we can have a finite gain version of first and second order. So then question arises that if I want a certain gain from the filter, then how do I decide gain of these smaller order filters? So there is no unique way. In fact, there will be multiple solutions possible for this case. So what we do is we have to decide how we distribute the gain for the total filter among various stages. So to keep the thing simple, we can assign the entire gain to one of the stages. So this is the simpler way, and this is what we will do in this case. And then once we have picked up the this transfer function, we denormalize with respect to the corner frequency and with respect to gain before we are able to set up the equation in for the unknown resistor and capacitor. And then we have to form the complete circuit or the complete transfer function by choosing the specific first order or second order. So even we have seen that for first order we have two versions, and up till now we have been using only silent key for the second order. But as I pointed out, multiple feedback topology is also possible for the second order active filter. So we have to choose one out of these two and create the complete circuit. And then we compare the individual transfer function of the circuit with the corresponding transfer function obtained from the table, of course, after denormalization. And then we set up equations for the unknown R and C. And then, of course, we finally solve the above equations by choosing values of some of the components, particularly the capacitor values. In some cases, we might have to choose resistor values also, especially for the case involving finite gain. So now let us take the example of Chebyshev low pass filter, and this is the specification for the Chebyshev filter. So what we have been given here is a pass band ripple of 0.5. So we know that Chebyshev filter will have this kind of behavior. So there will be ripple before it decays. So this is the ripple, and this ripple we know that in absolute value is given by 1 by square root epsilon square. So it is given that this value in dB is 0.5 dB. So that means 20 log of this thing. In fact, the magnitude, we are not mentioning the negative sign here. So this is one of the parameters, and bandwidth is 4. That means the corner frequency F naught is 4 megahertz. And then it says that at 10 megahertz, the transfer function must have decayed to minus 35 dB. And DC gain is 0. That means this value is going to be 0 dB. So everything below it is negative in dB scale. So this is the kind of filter that we have to implement. So now we are going to trace all the steps that we had listed there. So we have to decide whether active or passive. So in this case, we are taking active one, so that cascaded version can be implemented for higher order filters also, even though gain is 1. So we are going to choose the active version, and based on the ripple is given here. So in this case, filter is Chebyshev type. So now we have to find out what is the ripple factor, epsilon. So as I pointed out, this amount of ripple is dictated by parameter epsilon, and it is given by 1 by square root of 1 plus epsilon square. So what we have been given is ripple is given in dB scale, that is minus 0.5. As pointed out, gain is 0, so this is 0 dB, and below it at level of minus 0.5 we have the ripple or the corner frequency. So we set up this equation, 20 log of 1 by square root of 1 plus epsilon square is equal to minus 0.5 dB. So if you solve this, epsilon will turn out to be 0.349. So in this transfer function of the Chebyshev, this epsilon has been found out. Omega naught, or rather f naught, is already given, 4 megahertz. And what we have to now find out is this order of the Chebyshev polynomial Cn. So we now have to find out this order of the Chebyshev polynomial, and for that we will take the help of information given at 10 megahertz. So it is given that at 10 megahertz transfer function decays by 35 dB. In fact, it becomes minus 35 dB. So the transfer function is this expression. So 20 log of this thing is going to be minus 35 at 10 megahertz. So that is what has been done here. At f2, the transfer function value will be minus 35 dB. And f2 is 10 megahertz, f0 is 4 megahertz. Epsilon we have already found out, 0.349. So only unknown is the Cn or the order. But the Chebyshev polynomial is given by this expression. So here we see that Chebyshev polynomial has two different nature based upon the whether it is in the pass band or it is in the stop band. So if we want to evaluate it in the pass band, then we will have to take cos of n cos inverse omega by omega naught. And if we go in the stop band, then the transfer function becomes cos hyperbolic n cos hyperbolic inverse omega by omega naught. So here, from here we can find out n by setting up equation, which we will do. But this is one of the ways in which Chebyshev polynomials are represented in more compact form. But you might ask that we are always saying that it is Chebyshev polynomial, but we are not representing in that form. So it is possible to represent this Cn in polynomial form also. But here we will not do that because we do not know what is the order. So we know that the polynomial order will decide how many terms are there and what is the coefficient. So since we do not know this order of the Chebyshev polynomial, so we will not be able to pick the Chebyshev polynomial. So that is why we are going to use this compact expression in terms of trigonometric function. But there are tables which list all the Chebyshev polynomials starting from order n is equal to 1 to higher order. So here, please note that what we have been given is value at 10 megahertz, right? So this value at 10 megahertz, so this 10 megahertz actually falls in the stop band. So stop band starts from this corner frequency. Actually, there will be some transition band. So, but it is in terms of the mathematical expression of Chebyshev polynomial, it is divided into two regions. One region is this one where we have cos function, and another region is this region where we have cos hyperbolic. So this 10 megahertz actually falls in the stop band. So we are going to pick this cos hyperbolic function to set up equation for finding out n. So we now set up this equation. That means the value of the transfer function at 10 megahertz is minus 35 dB, right? So here we already know the value of epsilon. Omega is also known, 10 megahertz. Omega naught is 4 megahertz, in fact megacycles. So when we substitute this is the equation we get. So here you can see that we have everything known except this n. So we will have to do some calculation, and then we arrive at this equation. Cos hyperbolic square 1.567 into n is equal to this number 25,908. So if you solve this, actually n turns out to be this number 3.685. So since the order of the filter has to be an integer, positive integer, so that we can cascade a certain number of smaller circuits, so we take n is equal to 4. So here for the implementation purpose, n is taken 4. So if you take n 5, 6, 7, that will satisfy the chosen specification even better, but the circuit size will become larger. You will have to use more component. So that is why we do not try to take the order significantly larger than the that we get from this calculation. So we just round it up to the nearest integer and on the higher side. Right, so it has been now decided that order is going to be 4. So which will be equal to 2 plus 2. That means the overall circuit is going to be a cascade of 2 second order filters like this. So here we have our V in, and here we will have V out. So from the table, what we will find is the product of two second order transfer functions, individual transfer function, and their coefficients will be given by B1, A1, B2, A2. And here you can see that DC gain is equal to 1, and this S bar is actually S by omega naught. So we now go to the table. As I pointed out, in this case, actually there are going to be a very large number of tables. Theoretically, there will be infinite number of tables because any value of ripple can be chosen. So there is no restriction on the ripple value. It could be from a very small value to any dB. So there are infinite values of ripple possible. So there will be infinite tables. Since we have taken ripple to be 0.5 dB, so here is the table, partial table of the coefficients of transfer function for various values of n. So here we see that we are interested in the fourth order. So we will be picking up these coefficients here. So here what we have is this is A1 and this is B1 this is A2, and this is B2. So for the 0.5 dB, we pick up A1, B1, A2, B2 coefficients, and we then start the process of denormalization. But before that, we will take up the step 7, which is actually not required here. And since the filter is cascade of smaller filters, so the overall DC gain can be distributed among various stages. So this is the overall DC gain of the filter, and this now has to be splitted into various stages. In this case, among these two stages. Suppose so there was some gain, which is not the case here. So we will return to this point for the Butterworth case. Okay, so once we have picked up these coefficients, we have to denormalize the transfer function with respect to omega naught and gain, so that it can be compared with the circuit transfer function. So we first denormalize the S parameter, S variable, by substituting S bar with S by omega naught. So in this case, so now the corner frequency is going to be omega, and here corner frequency omega naught is 1. And then we denormalize with respect to gain. So we get the final transfer function. So this is the gain of the first stage, this is the DC gain of the second stage. Okay, so in this case, there are going to be two second order filters. So we have chosen two second order Sallen key filters with DC gain is equal to 1 for both the case. And that is why there are no resistors in the negative feedback path. So once we have done this, we will find out the transfer function of this circuit, VU divided by VI, and so the circuit transfer function is H1 into H2, where H1 we have already found out for Sallen key is given by this one, and H2 is given by this. So now this transfer function has to be compared with the transfer function of the denormalized version. So comparison for setting up the equation. So this is from table, and this is from circuit. So left side is from table. So we have already found out this one, and by now we have chosen what should be the gain. In this case, of course, it is going to be 1 because overall gain is 1. So now we compare the two sides. So when we compare denominator, this is the equations that we obtained, and we have already obtained these equations for Butterworth case in the previous lecture. So here you can see that we have only two equations and 4 unknowns. So we will have to choose some of them. So typically we choose capacitors. So we choose values of all these capacitors, and we have quadratic equation in R1 and R3. So that when we solve, we get R1, and R2 we take the negative part because we will get plus minus this. So plus is taken for the R1 and negative is taken for R2. Similarly here also R3 and R4 are obtained. And of course when we make choices for these capacitors, we will have to ensure that these two conditions are getting fulfilled so that this discriminant is greater or equal to 0. Now we come to Butterworth filter example. So in this case, the new thing that we have introduced here is you can see that at DC now we have a gain equal to 3 dB, right? So there will be a certain value. So for example, and then what is being said here that this is Butterworth type and with this kind of behavior. So what we will have here is 2.5 dB. So that means it decays by 0.5 at f1, which is 1 megahertz. And at 2.5 megahertz, what we want is 12 dB from the peak. That means this is going to be at minus 9 dB. So exact value is going to be minus 9 dB. And here we still have positive value, and the zero value will occur somewhere here, center frequency, minus 3 dB. So minus 3 dB means from the peak. So peak here is 3. So from here, it should be 3 dB. That means actual value here is going to be 0 dB. So up till now, in the previous lecture, we took a transfer function which actually started from 0 dB and then decayed. But now we have a gain of 3 dB. So this is going to be how the y-axis will look like, the transfer function values. So DC gain is 3 dB in this case. So all the steps that we took in the last class, they are going to be valid here. Only one additional step will come, that is distributing the gain of 3 dB among the various sub stages. So there is one change. Second change, of course, that will occur is the Sallen key will now have finite gain, and equations will involve more variables. So we are going to take active version of the circuit, and we have to implement Butterworth with DC gain of 3 dB. So first, of course, we have to find out order, and for that we try to take the help of the transfer function values at two frequencies, at 1 megahertz and at 2.5 megahertz to set up equation. So this is what is given, 0.5 decay at 1 megahertz, and it becomes minus 12 at 2.5 megahertz. So we have now these two equations, and equation 2 and 3, they are used to set up equation for the unknown n, and these two frequencies are given. So we find n is 2.62. So order that we will have to take is greater than this value, and this will turn out to be n is equal to 3. So now we have to find out corner frequency, because this will be used to denormalize the transfer function obtained from the table. So we take the value at 1 megahertz and solve the equation 2, and this turns out to be 1.42 megahertz. So since this is third order filter, so there will be one first order and one second order sub circuits. So the transfer function will have two smaller transfer function of first order and second order. So if you see the table for this case, for the third order case, then these are the coefficients given. So here you can see that although we have second order, coefficients are different than the previous case, Chebyshev case. So here we have a gain equal to 3 dB. Sorry, this is 3 dB. This is also 3 dB. So overall gain is 3 dB. That means 1.412. And now this gain has to be distributed among two stages, first stage and second stage. So what we are going to do is we are going to assign the entire gain to the second stage, and we will keep the first stage gain equal to 1. But as I pointed out, various combinations are possible for this scenario. So now we denormalize this transfer function that we have picked from the table. So we first denormalize with respect to frequency, the corner frequency, and then with respect to gain. And so this is final denormalized transfer function. So now we will set up the complete circuit by taking one first order and second order Allen key. But this time we will have to ensure certain finite gain uh, by using R3 and R4. So the transfer function is now going to involve two additional variables here, R3 by R4, and it will be there in the denominator also. So one has to re-derive this transfer function. It cannot be represented as a product of gain with the transfer function for gain is equal to 1 case. So now we compare these two cases. So this is for the first order filter circuit, and this is for the second order circuit. So from 3 we get gain is equal to 1, and RC is equal to A1 by omega naught. So from here we get R is equal to A1 divided by omega naught C. For the second order, we will have to, of course, first solve for the gain. So here you can see that one can solve for R3 as R4 into A02 minus 1. So this is already given. This has to be chosen. And then one can solve for the R3. Now for R1 and R2, we will have to take the help of these two equations. But here you can see that gain term is also present. So this can be substituted by gain minus 1. And then we will have the equation for R1, R2. And when we eliminate one of the registers, we get a quadratic equation. So that will lead to the quadratic equation in R1, and that can be solved for gain values. So that will complete the design of finite gain Butterworth filter. Now we come to a second circuit which represents a second order low pass filter. So here we have two feedbacks, one through R2 and another through C1. So there are two feedbacks, so that is why this is called multiple feedback topology circuit. And in this case, input is being given to the negative terminal of the op amp. So that is why this one is inverting circuit. So we first would like to convince ourselves that this one indeed represents a low pass. So for low pass, it should offer a finite gain at low frequency and very low gain or zero output at high frequency. So we'll see the equivalent circuit of this multiple feedback topology at DC and at high frequency. So we know that at DC these capacitors they are going to be open circuited. So now we have only resistors, and here you can note that resistor R2 is there for the feedback, and then we have here R3. So role of R3 is going to be ideally minimal, because we know that there is going to be no current in this input of the op amp, and this path is anyway open, so zero current through this, so zero current through R3. So R3 actually has no role, and this can be simply replaced by a short circuit under ideal condition. So we see that this simply gets reduced to one negative feedback amplifier case consisting of R1 and R2. And that is why in this case V out is going to be minus R2 divided by R1. So R3 has no role. Now if we see the equivalent circuit at infinity, then we see that both the capacitors, they are shorted. So in this case you can see now that this R2 and R3, they are in parallel. Their first end and second end both are connected together, so they are in parallel, so they can be substituted by single resistor with a parallel value, which will be R3 parallel R2. So here we can see that we have grounding of this node X. So here voltage is going to be 0. So now you can interpret this whole circuit as unity gain negative inverter amplifier. So here you can see that output is shorted to this part, right? So actually zero gain case. So we know that if we give any input here Vx, V out will be typically this say RF, this RF divided by R3 parallel R2. So this we know that it is going to be 0 because RF is 0. So we see that at high frequency output is going to be close to 0. That means it will suppress high frequency components, and that is why this is low pass filter. Now if we find out the transfer function, then then the transfer function will turn out to be like this, and here you can see that it is second order, and numerator is of 0th order. So this is a second order LPF, and the DC gain here you can see is equal to A naught. So this is the DC gain which we already derived from the analysis of the equivalent circuit at DC. So in terms of DC gain, we can write like this. So DC gain appears both in numerator and denominator, like that of the cell and key case. Right. So if one decides to use this multiple feedback topology for the second order transfer function implementation, then we will have to compare this transfer function with the denormalized version of the second order transfer function, and then design equation that we will get will be given by this. So here we compare with A2 and B2. That means this transfer function is compared with B2 S square by omega naught square, A2 S by omega naught plus 1. And here is going to be any gain that we have. So these are the two equations for four unknowns, C1, C2, and R2, R3. And for R2, or that means the feedback registers, these registers, what we are going to get is R2 by R1. So from here we can choose values of C1, C2 and solve for the unknown registers. And for unknown registers, there will be a quadratic equation. So R2 is given by this equation, and then R3 can be calculated from here. And with the condition, of course, that this discriminant should be greater or equal to 0, so that imposes restriction on what is the value of C2 we can choose. So references for this lecture are that op-amps for everyone, from where we took the table for the Chebyshev filter.